Hi everyone, welcome back. Today we're doing shortest distance to a character. We're given a string S and a character C that occurs in S, and we have to return an array of integers answer where the length of answer is the length of S. So an answer in every item in answer is the distance from index I to the closest occurrence of the character C in S. And the distance between two indices I and j is absolute I minus j, where absolute is the absolute value function. So it doesn't matter if the indices are before or after that given character, they will just take the distance between I and j like this. So let's look at an example to better understand it. So we have S, love Leetcode, and we have C equals to E. And this character E will occur in S over here. And we return an array of answers where answer.length is equal to S length. Okay, so this array, the output array, will be the same length as S. And each of these are distances to E. Okay, makes sense. L is 1, 2, 3 steps away from E. O is 2 steps away from E. L is 1 step away from E. E is E, so it has a distance of 0. And it's the same for the rest. L is 1 step away from E. And these two characters over here are E themselves, so they have a distance of 0. T is 1 step away. C is 2 steps away. O is 2 steps away as well. D is 1 step away. And E is 0 step away. Okay, so for the second example, we have 3 A's and 1 B. In this case, the distance between these 3 A's to B are 3, 2, and 1 respectively. And because B is the character itself, it will have a distance of 0. Let's look at the constraints. The length of S is from 1 to 10 to the power of 4. And every single character in S and C are lowercase English letters. So we do not have to worry about uppercase English letters. And it is guaranteed that the given C occurs at least once in S. Okay, shortest distance to a character. So off the top of my head, we can identify where the E's are. And if we do a linear scan in S from left to right, we will get where exactly each of the characters C are in S. Then we can do an expansion from there to demarcate the distance from each character to E. So for example, if we are at E and we expand outwards, we can determine the distances inside for each character. So we will do an expansion for each E over here. So in this case, if you have, let's say we have this strategy, S is equals to this test case and E and C is equals to this test case, we can do a linear scan across S first for char in S. And over here, if char is equals to C, then we will do some linear expansion here. So we will start to have a left and right index equals to, because we need the index of the current position, just the character will not be enough. So let's do enumerate on S to get both the index and character instead. So the left index in this case would be equals to, let's see, let's define a helper distance integer. Let this distance be equals to 1. And the left index in this case can be equals to index minus distance if index minus distance is more than or equals to 0, else let's define this as, let's give it a sentinel value. Yeah, actually we can just initialize this as none, and this index will be set if the index is, if this index minus distance is more than or equals to 0, in other words it's not out of bounds. And for the right index over here, we can similarly take index plus distance if index plus distance is not out of bounds on the right side as well, so less than length of s, else none. And the idea is we can set the distances in a given list. Let's call this shortest to char, and we can initialize this to be the same length as s. We will just give it a distance of, let's say, let's give it a very high distance, and because the highest distance possible is the length of s, so let's just take length of s multiplied by the length of s. So this is the maximum possible distance that a character can have from another given character. So let's say if e was here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this corresponds with the length of this string. So this length s is 12. So since 12 is the longest distance that we can have, let's set that to 12 instead. So this will be overwritten as we do this expansion. So now that we have the left and right index, we can set if left index, then we will set as left index equals to distance. How about that? So okay, looks great. Okay. Okay, looks great. So distance is equals to 1, left index is equals to distance, and if right index as right index is equals to distance. So we are currently setting, so let's say if you're at E over here, you are setting the left and right neighbors to be equals to distance 1, and you will try to expand the left and right index outwards to the point where both left and right index are currently out of range. And this distance would be incremented by 1 as you move both the left and right pointers outwards. And this iteration will stop once both your left and right indexes are not defined. So you can do while left index equals to the max of, actually this should be the max of itself. It is possible that the current distance for this given distance is already the minimum. Sorry, it's not the maximum, it should be the minimum because we want the shortest distance. So this would be right index distance, and we will continue to do this update as long as either left or right index is not none. So while left index and right index, then we will continue to do this. Sounds good. Or perhaps it's easier for us if we set the left index to be equals to the current index. No, actually that would be bad, right? Yeah, that would be bad. So distance is equals to 0. No, actually that would be a waste if we start off from the center or the current index as we do the expansion. So while left and right index, then we will do distance plus equals to 1. Then we will do left index minus equals 1. Okay, actually if left index, then if left index and index minus and left index minus 1 is more than equals to 0, then we will do left index. Okay. Actually, let's just copy line 11 and line 12 to be here. And we will just do this as usual. Yep, this looks great. So once you have both the left and right index, we will similarly do the same thing that we have on line 14 and line 15. And this will continue until both left and right index reaches the end of the list, where both your left and right index will be set to none. So this expansion will just keep happening until left and right index are no longer none. So it should be or. So this will continue as long as left and right index are defined. And this will continue for all characters. So this looks good. But as we can see, the current implementation is pretty long, and that's because there's some duplicate logic over here. There must be a way for us to edit this so that we do not have to do this first. So we can set in fact, we can just do index minus distance more than equals to 0 and index plus distance less than length s. So instead of defining left index and right index verbosely, this would work. So we can do this, and instead of this will work, and we will just put this at the back so that we will start off from distance 1, and we will let the next calculation over here determine the left and the right index. So in this case, we can just remove this and remove this, and we can just use index minus distance to be more than equals to 0. Then we just do index minus distance, and this, just by removing the left and right index convenience variables, you can shorten your implementation to a few lines like this. It does hurt readability because now the reader would have to know that index minus distance is your left index and this is your right index. But this will help with readability. This will help with making the code succinct so that it's easier to trace. So now that we have this implementation, we can try it with a simple test case and see how this works. So let's try this test case over here. I've already pasted it here, so let's give this a shot. So the length of s in this case will be 12 because we have 12 characters over here. So this will be equals to 12, 12, 12, 12. Okay, that's pretty long. So let's put that on a separate line. So I have 5 12s here, 6, 7, 8, 9, 10, 11, 12. So we have 12 12s here. We're assuming that each character over here is of length 12. And I just noticed that I missed one step. If character is equals to C, then we also have to set S at current index to be equals to 0. So looks good. Yeah, looks good. This looks good. This looks very good. Okay, looks great. So now let's start off with tracing line 10. So for line 10, index is equals to 0 and character is equals to the first character in S, which is L. And in this case, character is not equals to C, so we don't do anything. We will leave it to when we see character C to do the expansion and update the distances accordingly. So now character is not equal to C, so it skips. O skips, V skips, and now we are at E. So now we are at index 0, 1, 2, 3. So we are at index 3 and character is equals to E. And in this case, because C is equals to E, this is true. And let's continue. So now we set this current index at index 3 to be equals to 0. So let's just update shortest to character. And we set distance to a convenience variable of 1. And this current distance, this distance will be used to update the distances of adjacent characters from E right now. So V and L specifically, this will be used to set the distances of V and L to this distance value. So while index minus distance, this represents the left index, is more than or equals to 0, that's true. So index minus, for easier tracing, I will define two helper variables here, index minus distance. This is currently 3 minus 1, 3 minus 1, so this gives 2. And index plus distance, this is 3 plus 1, so this gives us 4. And currently, index minus distance, which is the left index, and is currently pointing at V over here, this is now equals to 2, so this is true. And index plus distance, this is 4. 4 is less than 12, so both are true, true or true. If index is minus distance is, sorry, it looks like I made a bug over here, so this should be checking for whether if this is more than 0. And index plus distance is less than length s. So we're just checking if these index are valid before we use them to update the distances in this shortest to char list. And looks like I also made a mistake over here. I should not be using s. I should be using shortest to char over here. So I have a lapse over here. So it should be like this. Thank goodness we traced this out. So now index minus distance is now true. So we set shortest to char. Let's trace it here. Actually, yeah, let's trace it here. Actually, no, it's okay. We'll just trace it in this list directly. So shortest to char, index minus distance, now this is 2. So at index 2, which is this character over here, representing the distance of V from E, is equals to the minimum of shortest to char in this same position, which is 12, as well as the distance. So distance is currently 1. So the minimum of 12 and 1 will give us 1. So let's update this distance. Now we will look at the second branch on line 21, index plus distance. This is currently index 4. So we are pointing at the distance of L over here. So this will be set to the minimum of itself, which is 12 and 1. So over here, we will update this with 1. And you get the idea. And from here, we will be incrementing distance by 1. And in that effect, this would now be pointing at index 3 minus 2. So distance is now set to 2. And we continue. So we are looking at V and E over here. So I noticed that perhaps there is an additional optimization we can do. If we notice that index minus distance in S is equals to C, then we can terminate the calculations as well, because we can leave it to the subsequent iterations to calculate the shortest distance. So if you encounter E on the right side, you do not have to really calculate and update the distances on the right. We will leave it to the distance to the other E's on the right to do the calculation for us. So it looks like on the right side, we could have terminated the calculations on this side if we encounter E as well. So that's one optimization that I did not think of. And now that we are tracing it, this actually gave ideas for doing that. So let's update this. So while index or this, or is there a way for us to, there's a lot of conditions to check if, yeah, let's just do left index. Yeah, let's just define two helper variables again, and let's see if we can abstract it such that we do not have to make our code too verbose. So let's just do left index and right index. Hopefully this makes it more readable. Index plus distance. And we'll just do while left index is this and right index is this. If left index is more than 0 and right index is less than 0, and we would use these indexes for the logic over here. And for the left and right index, we can just do minus equals 1, right index plus equals 1, and that's fine. And let's see. Okay, looks good. Or we can do something such that we check. We can set the right index to be out of bounds if we notice that the current character is equals to E. Then this way, you wouldn't execute this and this branch over here. So that makes sense. Let's try that for a moment. So we have the left index and the right index. Yeah, let's do this. If s at left index is equals to C, then we will do left index equals to -1. Else, we will do this. And similarly over here, if s at right index is equals to C, then we terminate the search by setting right index to be length of s plus 1. Else, this. So these increments will continue, is totally fine, but the logic would not execute, so that's okay. So with this little optimization over here, we're able to stop the expansion of the left and the right index if we encounter the current position to be equals to E. So looks great. Let's continue with tracing. So previously we stopped off at index 3, so left index is currently equals to index minus distance. So this gives us 3 minus 2, and this gives us 1. So 1 over here. So this is corresponding to O over here. So left index is equals to 1. Right index is equals to 3 plus 2. So this gives us 5. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5. So this equates to E. So we do this. Left index is more than equals to 0 because left index is 1. So we check if S at position 1 is equals to 0, and in this case this is O, so it's not equal to that. So we do oh, so we execute this branch over here. Got confused for a bit. So this is 2. Because this is 12, minimum of 12 and 2, this gives us 2. And let's check this. Right index is currently 5. So right index is indeed equals to C. So we will do right index equals to length S plus 1. So we basically stop the search, and we will leave it to the subsequent iterations at that index to set that distance to be equals to 0. So distance plus equals to 1. Again, this will be 3. Left index minus, so left index is currently 1. Right index is currently set to length S plus 1. So perhaps this can be set to, instead of just decrementing it, maybe we can just do max of left index minus 1 or -1. So it will not go below -1. So similarly over here, we can do right index equals to min of right index plus 1 or length of S plus 1. So this will just ensure that left and right index don't go beyond. And this is easier for tracing as well. We don't have to update left and right index once it's at the boundaries during tracing. So let's continue. Now left index is equals to 0, and right index is equals to length S plus 1. So because right index is more than equals length S plus 1, we will not be doing any subsequent calculations here. We will just be doing this. So now left index is more than equals to 0, so we continue. Since left index is indeed still more than equals to 0, we continue on line 21. S at position 0 is L, so this is not equals to C, so this will not execute. We will hit line 25, and now we will set this to the minimum of 12 as well as distance 3, so this will be set to 3. So we continue, and we are done with this iteration. This will terminate because left index will now be -1, and both left and right index are now out of bounds. So this will terminate for this current index equals to 3. So we continue along. Now we have L. So index is now equals to 4, character is equals to L. We continue. This is not going to execute because this character is not equals to E. So now we hit index 5. I guess another optimization is if you notice that the distances are, if the distances that you set is that you are setting is more than the current distance, then you can also set this to be equals to -1, because it means that you have already explored that distance, right? So this is also another hack that we can do. So we can do, instead of just doing this minimum over here, we can also do if shortest to character is less than, if the distance is less than shortest to character, then we can set shortest to character equals to this. else we will also use the same hack of setting the left index to be equals to -1. And the idea is that if you encounter a situation where the current shortest to character distance is already less than the current distance that you have, it's probably not worth your effort to continue updating the distances for subsequent characters on the left or on the right of where you're expanding from. So let's say you are here and you encounter 1 and you're trying to update this to 13. If this is going to be smaller than the current distance that you're already updating, there's probably no point updating the subsequent distances because you're just going to set this to a higher number. And the numbers over there on the left, the distances on the left are already small. So over here, we can terminate the search like this. So we can continue here. We can use the similar strategy in this branch as well. If distance is less than shortest to char right index, then we can do shortest to char right index equals to distance, and we'll add an additional else break here, and we will just set this to be equals to right index equals to length s plus 1. And this way we will terminate the search faster as well. So now we're at index 5. Where were we? And we were at distance 3, 0, 1, 2, 3, 4, 5. So we're now at 12. Okay, and we set this to be equals to 0. I didn't do it, I guess, just now for this E over here. Let's continue. Left index equals to 5 minus distance. So distance is now set to 1. And left index is now 5 minus 1, so that's 4. And right index is equals to index plus distance, so this is 6. So now we are like looking at 0, 1, 2, 3, 4, 4. So over here. So 4. Distance 1. So if in this case, since this is already set to 1, this will not be true. So we will set the left index to be equals to -1. So this branch will not be executed in the next iteration on line 20. And on line 29, right index less than length of 6. So no, this is going to be true. So this is true. I missed this trace earlier. Bear with me. And as right index currently for index 6, 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6 is also E. So in this case, this is true. And we will terminate the search as well by setting this to be 13. So 12 plus 1, 13. So this branch would not be executed now anymore as well. And this terminates, right? Yes, this terminates. So index 5 is done. We will continue to index 6. 0, 1, 2, 3, 4, 5, 6. So we're now here at this E over here. And character is equals to E. Oh, I didn't update the E just now, did I? Yeah, I didn't. So now this character is equal to C. So we will also set 0, 1, 2, 3, 4, 5, 6. This will also be equals to 0. And now distance equals to 1. Left index is equals to 5. Right index is equals to 7. So left index more than, okay, this is going to be true. Left index, yes, this is true. And in this case, left index is indeed equals to C because 0, 1, 2, 3, 4, 5. This is indeed equals to C, which is E. Left index will be set to -1. So we set this to -1. Distance less than shortest. Okay, no, this will not be executed because we ran line 22. We will continue on line 29. Right index less than length S. S right index equals to C. So what's index 7? 0, 1, 2, 3, 4, 5, 6, 7. This is T. So let's see. Okay, now so 7. So T, this is not going to be, this is going to be false because S right index is, perhaps I should just, yeah, actually, no, it's okay. It's okay. S right index is equals to, yeah, this is equals to T, right? So we will run this instead. So distance is less than, distance is currently 1. And distance 1 is indeed less than shortest to character at right index. Right index is 7. 0, 1, 2, 3, 4, 5, 6, 7. So this will be updated to 1. So this will continue. Okay. Okay, so right index is now equals to 7. So, and we just updated this, and this terminated, this whole branch terminated. Distance plus equals 1 on line 37. Left index is equals to left index minus 1 if it is not -1, so we leave it as it is. Right index equals to right index plus 1, so this is 8 now. So now we hit this branch over here again. Now we check is we updated T, now we're at C. So C is not equals to, the character C is not equals to E. So in this case, this is going to be true again. Sorry, this is not going to be true, this is going to be false. So we'll hit this here. So now the distance is indeed, distance of 2 is indeed less than distance 12 over here. So we'll update this here. We will continue. Distance equals to 3. Right index equals to 9. This will be set to 3. So now we are looking at character O. Sorry, this is still E. But right index is currently pointing at character O. So O in this case would be set to, O is not equals to E. O is not equals to E. So this will be set to 3. Minimum of 3. This will be set to 3. There's no minimum here. Sorry. This will be set to 3. And we continue. Distance will be equals to 4. Left index stays at -1. Right index increased to 10. So now 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're looking at letter D at right index. So D is equals to, D in this case is equal to, D is not equals to E. So we will hit this branch over here as usual. We will hit this specifically. And currently distance 4 is indeed less than the current distance of 12 for D. So this will be updated to 4 and we continue. So now we increment distance to 5 and now we are looking at character E over here. So now we will hit here. Right index is indeed equals to E. So we set right index to be equals to 13. So now we leave this to be updated later and we continue here. So now we are back to line 10 for tracing. We were at index 6, 0, 1, 2, 3, 4, 5, 6. We were here. Now we continue to index 7 and we point at character T. Is character T equals to C? No, false. So we continue. Character 8 is equals to C. this is still false. Character 9 is equals to O, this is still false. Index 10, character is D, this is still false. And finally, we are at the final index, index 11. This is equals to E. So now because character is equals to E, we will continue on line 12. So this is equals to 0. We'll set this to 0. And distance is equals to 1. Left index will be 11 minus 1. So this is 10. Distance we set to 1. Right index will be equals to 13. And yeah, I can remove that trace there. So left index is now more than equals to 0, but this is now less than length s. I mean, like, this will be false because right index is 13. So 13 is not less than 12. So this will be false now. So if left index is more than 0, okay, this is true. Now we check whether if this character here at left index is equals to C. No, it's not. It's not. D is not equals to E. So in this case, this would be false. We will hit this one instead. So now if distance is currently 1, is 1 less than 4? Yes, it is. So we will set this to 1. So this is true. We just reset it and we continue on line 26. Is right index less than length s? No. So this will not be executed. And we continue. Distance will not be incremented by 1. Left index will be 9 and right index stays the same because it is already at 13. So we continue. So now left index will be equals to, left index will be pointing at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We are pointing at O over here. So is distance at O, is distance at, okay, sorry, let's just start off from here. Left index is still more than equals to 0, okay. Is left index equals to C? No. So we hit this branch. Is distance of 2 less than the current distance at index 9? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. 2 is less than 3, so this will be updated to 2. And this will be true. And we continue. Is right index less than length s? Yes, it still is. So we skip all of this. Distance will now be incremented to 3. And left index will now be 8. Right index remains at 13. So left index is now 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Now we're pointing at C. Left index is pointing at C. And now we continue. Left index is more than 8, is more than 0, so this is still true. Is S left index at position 8 equals to E? Is C equals to E? No, so this is false. We hit line 22. Is distance of 3 less than shortest to character left index? No, 3 is not less than 2, so now this is false. So we execute this instead. Left index is now set to -1 and distance increment to 4. Left index remains unchanged, right index remains unchanged. Line 17 doesn't execute because both left and right index are out of bounds, and we terminate. And this is one long trace of this current implementation. But thanks to the tracing, we noticed a lot of optimizations that we could have done. So I would say this is a pretty good example of how tracing can save you during interviews. So for example, for this question, I did not see exactly how this algorithm could be optimized. So I hope that this was a pretty good demonstration of how tracing can save you. So let's check this output with the actual answer. So expected is equals to 3, 2, 1, 0, 1, 0, 0, 1, 2, 2, 1, 0. Yep, we got the answer. It's a very long trace. I could have done better, but I hope that this was a pretty decent breakdown of how you would do your best to implement this. So in this case, we traced it, and I will just implement everything in code again just to refresh the whole thought process. So the first step that we did was define a shortest to char distance, and this list of integers is the same length as s. So s is the string that's given to us, and this shortest to char represents the distance of each character in this string to the closest c. So in this case, we initialize this as length s, and this list would have the same length as s. And every single item in this distance is initialized to the maximum possible distance, which is the length of the string. So the next step afterwards is we did a linear scan across enumerate s, index char in enumerate s, and we started to check whether if the character is equals to c. And if the current character is indeed equals to c, then we use a two-pointer method to slowly expand and to get the left and right index. So left and right index will be equals to the current index plus or minus the distance, which is initially 1. And what we do is that we check if these current left or right indexes are equals to c. And if they are c, then we terminate the search by using this hack of setting the left index to be out of bounds. Else, we will check whether if the current distance that we're trying to set is less than the current distance that it already has. And if that is the case, we can also, in this case, then we would update the distance, else we will terminate the search by setting left index to -1 as usual. And we do the same for the right index as well. So we are updating the distances if it is less than, if the current distance that the shortest current distance that we can find is less than the current distance. Otherwise, we terminate the search by once again setting left or right index to be out of bounds. So then we increment the distance, and left and right index will continue to expand outwards till we terminate the distance. So it's like a expansion. So we would expand from e, these two e's here, and this e over here. And it will just keep updating distances as we go. So I got a bit too carried away. So let's quickly... So if the current character is equals to c, then we set the current... Oh dear, did I make a mistake here? Yes, I did. I should be setting shortest to char to be equals to 0 instead of s. So good thing that we traced here. Next thing is distance will be set to 1. Left index will be equals to index minus distance. Right index will be equals to index plus distance. And these are pretty much the left and right indexes that you're trying to expand. So while left index is more than equals to 0, or right index is less than s, if any of your left or right indexes are still valid, continue with this iteration of expansion. So if left index is not out of bounds, then in this case we will check if s left index is equals to c. So if the left pointer is already pointing at c, then terminate the search by setting left index to be equals to -1. Else, we set if distance is less than shortest to char left index. In other words, if the current distance is lesser than if the distance that we want to update with is shorter than the current distance it have, then update that distance. Else, in this case, we can terminate the search by setting left index to be equals to -1. So we will do the same for the right index as well. If right index is more than equals to, is less than length s. If right index is not out of bounds, we check whether if the current character at right index is equals to c. And if it is equals to c, then we will do right index. We will terminate the search by setting the right index to be length s plus 1. Else, we will check if the current distance that we're trying to update it with is less than the distance that it already has at the right index. And if that's the case, we update that distance with the lower distance. else we terminate the search by setting the right index to be equals to length s plus 1. And at this point, after the check on the left and right index, we increment the distance. And the left index will be equals to the max of left index minus 1 or the out of bounds index minus 1. Same for the right index, this will be the minimum of itself. We are trying to increment it, but if it is already out of bounds, then we will leave it as that index that is out of bounds. And at this point, this shortest to character should be ready to be returned. So this list s over here. So I will remove this tracing, and let's quickly look through to see if we have made any mistakes. So list n length s, we initialize the shortest to char list that represents the distance from every character at that position to the closest C. And we do a linear scan across S from left to right to check whether if the current character is equals to C. And if it is equals to C, we update the current character's distance to be equals to 0. And we proceed to use that window method to continuously update the distances of its adjacent cells. And as long as the left and right index are not out of bound, we will continue to do this expansion. And we make two optimizations. We check if the current string is already equals to C on the left or the right index. Then we will terminate the expansion for the left or right by setting the left or right index to be out of bounds. The second condition for terminating the search is if the current distance that we're trying to set it to is already equals to or more than the distance that it already has. So on that note, if that's the case, then we also terminate the search by setting the left or right index to be out of bounds. Else, we update the distance for that character from C to the lower number. So once we're done, increment distance as usual. This distance will be used to update the distances in shortest to char in the next iteration, and we move the left index to the left and right index to the right, and the cycle continues. And once we're done, we should get the answer. So let's run this against some test cases. Woo, passed. Let's submit this. And there we go, we got the answer on first try, which is pretty good. So in summary, the time complexity in this case would be at least ON over here. But because we also do the left and right expansion over here, in the worst case scenario, this would be ON as well. Imagine expanding from the rightmost character over here. You might end up expanding all the way and iterating a left scan, linear scan from right to left over here. So this can be ON as well. So in summary, unfortunately, this theoretical time complexity is ON square. And the space complexity in this case, let's take a look. Let's remove the markers for time complexity. We use ON space to keep track of this copy of shortest to char. This list will have the same length as S. Sorry, I didn't mention this earlier, but N is the length of S. So if your S increased to 100 characters, then shortest to char will also be 100 characters. So this is ON. We use ON space here. It scales linearly with N. And in this case, we only use single variables to keep track of indexes and distances. So this is constant space. Looks like we do not use any other variables that scales linearly with N. So space complexity will just be ON over here. So that's pretty much it for this question. Took me quite some time to trace. Looking back, I could have done this better. But since this is the first time I was looking at this question, I think that's a pretty decent try. So thank you so much for watching. If you find this useful, please give us a like and subscribe, and we will see you in the next video.